Good morning, students. Today I'll be explaining crystal oscillator and parallel resonant mode. In the last class, I have discussed about transistor crystal oscillator and the transistor crystal oscillator operating in the series resonant mode. Okay, this is the series resonant mode of the transistor crystal oscillator. So in the parallel resonant mode, as we can see in this figure, the crystal is connected in parallel to the tank circuit. This is the crystal here, right? This is the crystal, and this crystal is connected parallel to the tank circuit. Okay, and hence it is called as parallel resonant mode because the crystal is connected in parallel to the tank circuit. R1, R2, and RE resistors are used to set the desired operating point. The resistors R1, R2, and RE are used to set the desired operating point. Then the radio frequency choke coil, RFC coil, it passes only the DC signals and it suppresses or it blocks the AC signals. Hence, the oscillations are prevented from entering into the VCC, or the oscillations are prevented from entering into the supply VCC. Then the bypass capacitor here, C2, right, is in series with the C1. So this C1 and C2 act as a voltage divider circuit. There's a voltage divider formed between C1 and C2. The voltage across C2 is fed back to the emitter terminal. The voltage across this C2 capacitor is fed, or it is fed back to the emitter terminal. Okay, so like this, there is a feedback established from the capacitor C2 to the emitter terminal of the transistor. Then there is the capacitor CB, coupling capacitor CB here. So this coupling capacitor CB acts as the AC signal ground, because if there is any oscillations or AC signal present, that is shorted to the ground, because we know that the capacitor passes the AC signal, or it shorts the AC signal to the ground here. Okay, hence there is no feedback formed at the base terminal. There is no feedback at the base terminal from the output. Okay, there is only the feedback from the capacitor C2 to the emitter terminal of the transistor. Okay, crystal is used as a shunt element in the tank circuit, or it is connected in parallel so that it operates in the parallel resonant mode. Tank circuit is same as that Colpitts oscillator. So if you can see this circuit, the tank circuit is same as that of the Colpitts oscillator. The Colpitts oscillator, we are having what, students? C1, C2, and L. Here instead of L, we are having a crystal. That is the only difference between Colpitts oscillator and the crystal oscillator in the parallel resonant mode. Fine. Maximum voltage is developed across the crystal. So here, as it operates in the parallel resonant mode, at the parallel resonant frequency of P, we know that impedance is maximum. Right? We have seen in the last class the graph. Okay, in the graph of the last class figure, we can see here at FP parallel resonant frequency, at FP the impedance Z is maximum. So as the impedance is maximum, the output voltage is also maximum. Okay, because of large value of impedance. So as the output voltage is maximum, and hence the feedback voltage is also more. The feedback voltage is also more from capacitor C2 to the emitter terminal of the transistor because of maximum output voltage. Here the crystal behaves as an inductor at its parallel resonant frequency, because we know that at the crystal oscillates or produces sine wave oscillations, right? When it is inductive in nature, when the crystal is inductive in nature, it produces sine wave oscillations, or the oscillations at its parallel resonant frequency. Hence, the crystal behaves as an inductor as its parallel resonant frequency. Here, the oscillations that are produced at or formed at the parallel resonant frequency, they are sustained oscillations or stable oscillations. They are formed at the parallel resonant frequency. Hence, sustained oscillations or stable oscillations are formed or produced. If there is any change in the supply voltage or transistor device parameters, then that does not have any effect on the frequency of the circuit. Change in the supply voltage or change in the transistor parameters does not have any effect on the frequency of the circuit. Okay, because it is a stable frequency. Because of the high stability of the crystal, the frequency stability of the circuit is also high, and hence if there is any changes in the supply voltage or any changes in the transistor parameters, that does not have any effect on the frequency of the circuit. Fine. So this is about the crystal oscillator in the parallel resonant mode. In examination, the question can be explain the operation of the crystal oscillator in the series resonant mode, or explain the operation of the crystal oscillator in the parallel resonant mode. Now, what are the advantages, disadvantages of the crystal oscillator? The advantages or merits of crystal oscillator are: it has high frequency stability. Frequency stability is high. A change in the frequency is just 1 hertz for 1 megahertz crystal per day. The drift or change in the frequency for 1 megahertz crystal is just 1 hertz per day. Hence, it is negligible. Crystal with frequency of up till 10 megahertz can be constructed with very high stability. Frequencies, crystal with frequencies up to 10 megahertz can be constructed with very high frequency stability. Temperature stability of the crystal is also very high. That means change in frequency for the change in temperature is very negligible. Quartz crystals are readily available in nature, and these crystals are small, they are having less weight, and they are cheaper, they are less expensive. Okay, so these are the merits or advantages of the crystal oscillator. And one more advantage is that crystal replaces the inductor in the tank circuit, and hence the crystal oscillators are having less weight and they are less expensive, or they are cheaper. Coming to the disadvantages or demerits of crystal oscillator, crystals are delicate. As we know that crystals are delicate and hence require careful handling. We know that the resonant frequency or the frequency of the crystal is inversely proportional to its thickness. That is, as the thickness increases, frequency decreases. So if you want high frequency, then the thickness of the crystal should be very less, which makes the crystal mechanically weaker. Okay, the crystal becomes mechanically weak when its size is very less, when it is very much thin in size, because of requirement of high frequency. When we require high frequency of the crystal, the size of the crystal becomes very less, very small, very thin, and hence it becomes mechanically weak. Frequency of the crystal depends on the dimensions of the crystal and also on the orientation of the crystal structure. Hence, for a given crystal, the frequency of oscillation is fixed. If we want a different frequency, then we have to change the entire circuit and replace the crystal with the new crystal. Right? So these are few of the disadvantages or demerits of the crystal oscillator. Coming to the applications of crystal oscillator. What are the applications of crystal oscillator? The crystal oscillator is used to generate the oscillations or the clock signals for computers and other synchronous digital systems. It is also used to generate carrier frequency in the communication transmitters, to generate frequencies or local oscillator frequencies in communication receivers, and crystals kept in temperature controlled ovens is used to generate high precise clock, high precision clock, which is used for time measurements. Crystal kept in temperature controlled ovens is used to generate high precision clock, high accuracy clock, which is used for measurement of time. These are few of the applications of the crystal oscillator. Next, we will see one example on crystal oscillators. Take this example. A crystal has following parameters: L equal to 0.334 Henry, C is equal to 0.065 picofarad, that is capacitance. They have given inductance, capacitance, Cm, that is mounting capacitance, it is 1 picofarad, then resistance R is 5.5 K. So they have given all these parameters, that is inductance is given, capacitance, resistance is given, and the mounting capacitance is also given. Next, then what we are supposed to calculate? We are supposed to calculate part A, series resonant frequency. Then part B, calculate parallel resonant frequency. Third one, by what percentage does the parallel resonant frequency exceeds the series resonant frequency, or by how much percentage the parallel resonant frequency is more than that of the series resonant frequency. That we are supposed to calculate here. Now, all the formulas are readily available for us. We have already derived the formulas for series resonant frequency, parallel resonant frequency. So let us make use of the formulas for our calculations. So Fs, that is series resonant frequency, is given by Fs is equal to 1 upon 2 pi root LC. It is 1 upon 2 pi. L is given 0.334 Henry into capacitance is 0.065 into 10 raised to minus 12. So this, if we calculate, it comes out to 1.08016 megahertz. Right? That is 1 upon 2 pi, 1 upon 2 pi into square root of what is the inner term of the square root? 0.334 into 0.065 into 10 raised to minus 12. Okay, so this comes out to how much? That is, answer is 1.08016 megahertz. Okay, 1.08016 megahertz is the answer. Fine. Now what about the frequency in terms of radians per second? So it is, omega is given by 2 pi f s or 2 pi f, that is 2 pi into 1.08016 megahertz. So in terms of radians per second, the frequency is 6.7868 mega radians per second, that is 6.7868 into 10 raised to 6 radians per second. The next part, that is part B, parallel resonant frequency. We know the formula for parallel resonant frequency. It is Fp is equal to 1 upon 2 pi square root of LCP. Fp is equal to 1 upon 2 pi square root of LCP. What is Cp, students? Cp is equal to CCM divided by C plus Cm. I hope everyone are following here. Yes. So Cp is equal to C into Cm divided by C plus Cm. C is 0.065 picofarad. They have given. They have also given the Cm value, that is 1 picofarad. Substitute that, so that will be 0.065 picofarad into 1 picofarad divided by 0.065 picofarad plus 1 picofarad. This comes out to 0.061 picofarad. The value of Cp, it is 0.061 picofarad. Substitute this value of Cp in the previous equation for Fp. That is, Fp will be equal to 1 upon 2 pi square root of L is 0.334 into Cp we have calculated just now, that is 0.061 into 10 raised to minus 12. So if we simplify this, then we'll get 1.1150 megahertz. The value of parallel resonant frequency is 1.1150 megahertz. That is 1.1150 into 10 raised to 6 hertz. Then in terms of radians per second, omega p is equal to 2 pi fp or 2 pi f. That will be, if we calculate this, 2 pi into 1.1150 into 10 raised to 6, it comes out to 7.005 mega radians per second. That is 2 into 3.142 or 2 into pi into 2 into 3.142 or 2 into pi into 1.150. Okay, 2 into 3.142 into 1.1150. So that comes out to 7.005 mega radians per second. Fine, students. The next is percentage difference between Fp and Fs, or by how much percentage Fp is more than Fs, or parallel resonant frequency is more than the series resonant frequency. So it is Fp minus Fs divided by Fs into 100%. Substitute the values here. Just substitute the values. So whatever we have got, okay, that is 1.1150 minus 1.08016 divided by 1.08016. That is whatever we have got Fp and Fs, I have just substituted in this formula. So it is a percentage difference, okay, between Fp and Fs with respect to Fs. So if this comes out to 3.22%, that means the parallel resonant frequency is 3.22% times more than that of the series resonant frequency. The last part here, that is quality factor. We are also calculating the quality factor. Quality factor, as we know that more the quality factor, less will be the distortion. So here, and high will be the stability. So quality factor Q is given by omega s into L divided by R. We already calculated omega s. How much is omega s? Yes, please. So omega s is 6.7868 into 10 raised to 6 radians per second. Substitute this. So this will be 6.7868 into 10 raised to 6 into 0.334 divided by 5.5 into 10 raised to 3. So I have substituted omega s, L and R. So that comes out to 412.14. So this much is the quality factor of the circuit that is connected for the crystal oscillator. Okay, so in today's class, students, we have gone through, that is crystal oscillator and parallel resonant mode, right? Crystal oscillator and parallel resonant mode. Fine. Then we have also discussed the advantages and disadvantages of crystal oscillator, applications of crystal oscillator. Then we have covered one example on the crystal oscillator. Okay, an examination on the example may be asked on the crystal oscillator. So similar examples may be asked with the just change in the values of L, C, Cm, and R. They may give different values of L, C, Cm, and R, and they may ask you all to calculate the series resonant frequency, parallel resonant frequency, and by what percentage does the parallel resonant frequency exceed the series resonant frequency and its quality factor. Fine. So I hope everybody have understood here. If there are any doubts or any questions on today's topics, please send your doubts and questions to me. I will answer to your questions and I'll also clarify your doubts. Thank you.